Clay, that's going to take over the presentation in a few minutes, he has several slides that will talk about the digital twin. And then he'll talk about how STAR-CMM Plus with HEEDS fits into this vision. And HEEDS is a journal optimization program that integrates into STAR. So, and he has two presentations on how he has used this coupling and how we use STAR.
Good.
Okay, I'll get out of here.
So we will move forward.
Thank you.
First off, I'd like to start off with this slide here. We really like the video on it. This is a concept IAA vehicle that was developed by Mercedes-Benz. If you notice the graphics, it has some interesting designs to it. It switches from a design mode to a performance mode at about 80 kilometers per hour by extending some aerodynamic features out at the rear of the vehicle. Now, one thing to mention is all the aerodynamics for this vehicle were developed in STAR-CMM Plus using the Design Manager HEEDS optimization capabilities. The engineers at Mercedes-Benz, they tested over 300 design variants to come up with this design. This design has set a ultra low drag coefficient of 0.9. I don't think the record on that has been beat yet, but more importantly, they were able to reduce the time of concept generation by over 50%. And this is something that is the direction that's going throughout all of CFD and probably design analysis and simulation in general. And Mercedes-Benz has actually extrapolated this simulation process to all their production vehicles. So I kind of want to bring up this slide here, and this slide is geared towards the vehicle market and development within the vehicle market, but to a certain extent, it could be transferred to any industry. Kind of going from the left to the right, you've got the pressures on the designers within the vehicle market. This is decreasing emissions, decreasing overall CO2 output in order to meet targets for reversing greenhouse gas emissions. Many of these regulations are applicable to other industries as well. It's just outside pressures being put on the designers. Within the vehicle market, this is really being transferred to a move towards electrification of the vehicles themselves. And there's lots of applications for CFD within vehicle electrification. As mentioned before on the previous slide, you've got to calculate the drag coefficient on a vehicle, and that's just a classic analysis to do. But in addition, you've got to assess, thermal comfort of the passengers. You've got conjugate heat transfer within the vehicle itself through the motors, the electronic cooling systems, and the battery systems as well. It's a very complex multi-system problem that needs real-world analysis solutions. But most importantly is over on the far right, reducing cost and time. And typically when you think about an electric vehicle, you're thinking of the costs associated with the main components, the battery costs, the motor costs, which usually gets overlooked. And there's been lots of improvements to these items throughout the years. Lithium-ion batteries have gotten cheaper over the years. They've gotten more power dense. That's enabled increased range of vehicles. It's then brought down vehicles to be affordable for mass public. But the one thing that's usually missing in all this is the amount of time and effort that goes in on the engineering design process. This time and effort is built into the cost of these vehicles and affects the bottom line. So anything you can do to reduce this time and effort is going to be much benefit to the companies that are producing these vehicles.
Hey, Clay, this is George. I want to jump in real quick on that slide. The reason why the Siemens put that slide in because STAR has a whole nother module set up for doing batteries, for battery efficiency and chemical reactions. And So that's another, you know, they like this because electric motors generating the heat. And so STAR really fits into the whole electrical vehicle story, you know, fits in. But again, the digital twin and cutting the development time from the Mercedes on down to the electrical vehicle. So they're focused on this. So, okay, your next slide is my favorite. Onward.
Okay. Yeah, this next slide, it talks about how do engineers usually spend most of their time, especially simulation engineers. Typically, you'll see something like this. You've got build, test, explore, and assess the design space. You know, as a simulation engineer, you're spending most of your time in building and testing. You're putting together the models, you're trying to test and debug them. By the time you get a solution and you can actually do some exploration and assessing the design space, you've usually hit the end of the project. You've got to wrap everything up and move on to the next fire. If you look at, you know, how much value you could extract out of this, most of your value is going to come from exploring and assessing the design space. You know, that's where you're going to find your optimal design, your optimal solutions to the problem. Most of the time, you're just kind of running a few cases to see whether or not you have a design that works, a design that will meet the requirements, a design that won't fail. You might be missing the designs that would maximize your reduction in heat, you know, maximize your thermal performance or any other metric that you're going after. You're mainly just looking at the baseline requirements. So the question is, how do you align these two curves? How do you make sure your engineering time is extracting the most value? And that's where, you know, the design automation and optimization algorithms come in. And there's 3 keys to that that's offered by Siemens. You know, the first key is developing the tools, the design analysis software like STAR-CMM Plus that can analyze complex real-world problems. And then the second 2, you know, offering flexible licensing models. We'll explain that a little bit more, but basically, CFD is computationally demanding. You need to run on as many cores as possible, and the licensing models offered by Siemens tries to make this possible. They're geared towards parallel computing. And then, of course, there's individualized customer support. CFD is a large world that you can easily get stuck in, so the focus on is developing a personal relationship with the user to make sure that they can overcome their problems and challenges.
Yeah, and this is George again. It's somewhat unique in the model. In the FAA world, it's a mature enough technology, and I want to say usually you get stuck just building the damn model and trying to get it out the door. CFD, it's a little bit like building the model is usually not the hard part. It's getting through the runs. It's getting all the analyses done and doing the what if scenarios, because so many different variables can change, and that's why it works so well for this optimization scheme and extracting the value of how you say moving the exploration up front at the very beginning to extract that value, and that's why it's found success in the CFD world. And in the FAA world, it's been more stuck, because if you make design changes in the structure, oftentimes you have to rebuild the whole model, so it's much harder. That paradigm is not fitting as well. And so back to the CFD, on the technical support, it is quite unique. It's part of the cost model. Yes, it's flexible license, but it costs more because it's a whole package. You get pretty much a dedicated support engineer along with it, and you need it. I mean, we need it for our projects. We're not the only ones calling it for support. So, thanks, Clay. Back to you.
All right. So the focus is on STAR-CMM Plus, and there's a number of features within this that enable, as they say, discover better designs faster. The first aspect is the implementation of parametric models. So built into STAR-CMM Plus, it has its own 3D CAD tool, which is actually a pretty solid 3D CAD tool in my experience. There's a lot you can do with it. So with this CAD tool, you can identify certain parameters, certain dimensions within your model that you'd be interested in changing. You make those parameters. Within the CFD tool, you can identify different aspects of the model or different assumptions and certain parameters within the model to make those points and focuses of study. You can also link to exterior CAD tools like NX, and also bring in geometry from pretty much any other CAD tool out there as a native or neutral format. One of the biggest strengths of STAR-CCM Plus is a flexible, robust meshing. It was a pioneer in developing polyhedral meshing. This is a superior form of meshing, especially for handling swirling flows to make sure that your flow is perpendicular to the face as it's crossing through the cell. In addition to the polyhedral meshing capabilities, it has a surface wrapper too. So the surface wrapper enables you to basically bring in nearly any geometry that you have, no matter how complex it is. The example that they have in their demo setup is bringing in a motorcycle that has all the little features of the handbrakes, items like that. You can apply a surface wrapper to that instead of trying to clean up that geometry, and use the surface wrapper to basically create another mesh above it and use that as your basis for your volume mesh. It really optimizes and streamlines the workflow and allows you to reduce time up front. STAR-CCM Plus has a wide range of multi-physics capabilities. Kind of examples here on the right side of this chart. You've got traditional conjugate heat transfer that's shown in the upper left and flow problems, but also you've got dim modeling capability. You see this little graphic of the kind of a hopper on the center left of these images. You've got combustion, as we've mentioned before. We've been trying to get a little bit into combustion this past couple months at Predictive. You've got volume of fluids, which is very popular has a lot of use in the marine industries. And of course, you incorporate motion into your CFD problems as well. And as George mentioned, there's a battery module out there for electric vehicles. As briefly mentioned before, STAR-CCM Plus is geared towards parallel computing. Normal CFD analyses, they require, running on multiple cores, running on as many cores as possible. And when you start getting into design studies, what you're going to want to do is try to run as many design variants as possible in parallel on parallel cores. They've tested and benchmarked STAR-CCM Plus to run on 100,000 cores on an NCSA supercomputer, as you see here in the lower right, and it's ran with a very high efficiency versus kind of an ideal rate. Workflow is completely automated in this process. This is the key to the parametric models, as mentioned earlier. Once you've parameterized your model and your model setup, you can easily adjust dimensions, remesh, reanalyze, and spit out the results that you want. And finally, integrated within STAR-CCM Plus, within the Design Manager, is HEEDS for design optimization. The optimization algorithm within STAR-CCM Plus is a hybrid algorithm that not only tries to identify the best point for your design, but tries to identify the best path and best optimization routine to get to that point. So I want to go here over the process of how virtual prototyping works in STAR-CCM Plus. And the first part is you've got building the model. I believe most people would be familiar with this. You bring in the CAD geometry. It can be built in within a 3D CAD tool, or it could be imported from an exterior CAD system. You mesh the region of interest that you're interested in, and then you move to test. In test, you set up your physics, define the physics that replicates what you're trying to simulate. You define your boundary conditions, and then you run your analysis, do your post-processing, and get out the variables of interest. And this line right here is typically what most simulation engineers do. But to fully explore the design space, you need to look at how you close that loop. And that's where you get into the optimization. So with optimization, you're going to define what parameters would we like to study on the original model and what is our design goal. You identify the parameters, you identify the limits on the parameters, and then you define what you want to optimize. So in the example here, we were looking at the rear wing on this Le Mans race car. They're looking at the tilt of the wing, the axial position of the wing, and they want to know what the drag force and total downforce on the vehicle is. And once you've defined that, you run this in an automated loop. And the software will automatically go through the design space and try to identify the best performing designs. And you see here in the lower left, there's a plot that's being generated of the optimal designs and the development of what they call Pareto front. And this would be the best trade-offs in lift and drag that you can attain. So what we'd like to do right now is kind of switch over to a couple of examples that we've developed at Predictive Engineering to discuss how this is actually used in STAR. How do you put this together? And first one is a flow mixing problem. It's from an old HVAC job that we had some years ago.
Yeah.
And the way this is set up.
Hey, Clay, I'll jump in because that's mine.
Okay.
Wind turbine is yours. So this is the one I did where I said the classic, well, we'll run 10 revs and 10 changes and check each one. Yeah. And I never got anything really good with it. So it was just too good an example to bring out. So I said, okay, Clay, you got to do this. Show me how to set it up. And what they're doing, it sits on top of a hospital roof. It's the air mixer of return air and new air mixing in before it goes into the heat exchanger racks. And you really want to get thorough mixings. You want to avoid having streams of cold air coming from the outside and streams of return air. And if these streams do build up, if you don't get mixing, they'll stay that way and they're actually going to the ventilator and you get hot and cold spots inside the system. So the mixing, usually you have to have very large spaces and you have these blades that are set up to turn it. So this was an advanced mixing design where you're shooting in the external air down through the baffles. Those are through the columns, and the return air from the hospital are just coming in through the wide spot. And you got different temperatures and different flow velocities. And so the slots, go ahead, Clay. This is where you can jump in. You set up the slots with different flow resistances on it.
Yeah, the slots are, you've got the 6 columns down here. We've got about 5 baffles. They're modeled as porous baffles with different resistances. So the question is, what are the appropriate settings for those flow resistances?
Yep.
And the second example is a wind turbine. This was something, I was researching through literature, trying to put together something real quick that we could run an optimization study on, and I came up with this design that was real interesting. This is for harvesting wind energy, and basically they're putting these cowlings around the turbine blades themselves. So the idea is you're kind of trying to create some negative pressure here to increase the flow velocity through that turbine blade. In wind energy, the amount of power you can extract from the airflow is actually going to be cubed with the air velocity. So anything you can do to increase that air velocity through here is going to allow you to more efficiently extract power from the air. So this is somewhat traditional airfoil design. And a good question is, what is the optimal shape? What's the best shape that you can come up with that's going to maximize the velocity through here? And also, decrease the amount of total drag force that you would have on this, because you've got this thing sitting maybe 10, 20 meters up in the air. So you'd like to reduce the amount of drag on that too. So let's jump over in STAR for the first problem that we had mentioned on the flow mixing. As you can see here, we have the geometry. The original geometry that we showed before had 6 channels. Pretty much everything is symmetric to one another, especially once you get into the center channel. So we've cut this down to take advantage of symmetry. And we can see here, if I explode out the boundaries, the way the model's set up, we've got those two sides right here that are planes of symmetry. We've got the return air inlet. This is return air from HVAC system at 24 degrees C. And then we got cold exterior outlet air at minus 11 degrees C. As mentioned before, we've identified 5 baffles that go down the length of this column. And each of these baffles has a resistance associated with them. That's shown right here. So we've parameterized these resistances, and there's many resources out there. We've used idle check and Freed in the past that give you hand calculations for associating resistances with certain densities of a screen mesh or a pattern of holes. So there's engineering justification for kind of going back to a simplified model such as this. And we can open up here some initial design results. We started off with a value of 5 for each of these baffle resistances and ran the model to a converged solution. You see kind of the general trend what we have right here. We've got the cold air that's coming in. It's actually getting pushed down to the bottom. Most of the warm air is getting channeled in the middle. Some of it's getting pushed up. And overall, we don't really have very good flow mixing. If we look at a plane about 3 meters downstream from those channels, we've got about close to 3 degrees C delta T throughout that plane. So overall, we'd like to, lower that gradient if possible. And what we're using is a statement right here is we're looking at the standard deviation of temperature in that plane. So one thing that you can do that George may have done before when he was doing this project is you could start running this project. We could go to these baffles right here and start adjusting the numbers of them and see what the changes would be.
That's what I did, pretty much.
Yeah. And you can imagine engineer doing this is going to spend hours and days just putting on different numbers, and driving it in the wrong direction right here. So I would say overall, this is not a very good method to pursue.
No, it was my beer project, because you just pick some numbers. I watch it, drink a beer, watch it go by, give up.
Yeah. So what we did was we put it into the design manager in STAR-CCM Plus to see what kind of solution that we could get. And this is the design manager here where we've declared optimization study for this. We have our input parameters here. It's those 5 baffles, and we can set the range for each of those. And then we have the responses that we're worried about. So this is the standard deviation of temperature in that plane. And I also put up the back pressure on here because we probably want to minimize the back pressure on the HVAC unit.
Good.
And this is a single weight study. So both of these points are being added up into a single cost function that the optimizer is trying to find the lowest value to. And we ran this through 160 design cases. And you can see over here, this is the square right here is where we started off on the initial design. And every time it finds a better design, it makes that its holding point and continues searching around the solution space. And I think we get down to over here about design 145. And I can open up the temperature distribution in that plane about 3 meters down from where we started. And where we started, close to 3 degrees C delta T, we're now down below close to half a degree C delta T right here. So it's been a great improvement of where we started versus where we are right now. And it took me a few minutes to set up this optimization study, and you hit run and go off and do something else with your time.
Yeah,
so let's talk about.
I want to say, okay, yes, simple model, and people can nod their heads. I say, yeah, our models are huge and gigantic, take a long time. But that's one of the things is STAR goes, you can send it off to the cloud if you want to. The licensing model is not a big deal, and you can run it that, or with it, we have a workstation with 38 cores locally, and it chews. I mean, it goes well. I mean, once you get something set up, you can run much larger model through it, and it may take a day, overnight, 2 days. But then again, if it's truly gigantic, and once you have it worked out, you can send it to the cloud. So, technically, back.
So the previous model, we were looking at a design parameter within the model. So what happens if you have to change the shape and remesh the shape? So here's our airfoil right here where we're meshed. You know, we've got some refined cells down at the front where we're hitting and trying to refine a wake zone behind it. Here in the design parameters, I've got 6 parameters listed. If I go to the built-in 3D CAD tool, as seen here.
Is this 2D or 3D?
This is axisymmetric.
Axisymmetric.
So,
oh yeah, it would be.
You revolve the 3D and then get a 2D plane out of it.
Good for you.
So as you can see here.
I want to mention too. It's. I mean, this is purist, but STAR, since it's part of the course Siemens PLM software, digital twin. You know that you can hook it up to NX too, and well, we'll do that. We'll do it in the next project. But that's one of the gigs. Of course, you hook it up to NX, and it will feed parameters back and forth. You know, and you can change your geometry on your huge model and bring it back into STAR. And I want to say one of the enabling technologies that makes it next generation is like STAR will actually mesh crap. Before they would say, oh, you can do a demo, and anytime you make a geometric change, it would blow up your mesh. And it's like, you know, fine. It's just a cartoon, demo cartoon. But what's different is that the meshing technology in STAR is really standout. It's one of the it's enabling technologies is the wrapper. Clay talked about it. Eliada has this cool wrapper that thinks. Well, a lot of people, they talk about wrappers, but in CFD, you really have to have it because very tiny features don't really affect anything on your mesh usually, and if you can just blend those together, you cover it with a skin, it's going to be a lot better numerically, and you're going to better solution. It also enables you to take very large assemblies and do these parametric studies, these optimization studies, because the wrapper is integrated into the tree. And so when you bring it in, we make the parameter NX, it brings back the geometry in, and it'll automatically reapply the wrapper, send it through the tree, and boom, into the optimization. So it's much more than a sketch. This is one option. Okay, back to you.
Yeah, so in the sketch here, I was trying to guesstimate that airfoil design from the paper. Truthfully, in putting this model together, I probably spent more time trying to put this sketch together than actually set up and run the optimization study itself. But we've identified about 6 different geometric features that we could use to guide the sketch. Everything's back to geometric constraints. And we've called those out as the parameters here. And again, you know, we've got an initial solution that we've run. And again, we could pick this solution up and start running it again. Or we could, make some changes here to these parameters. So maybe we increase that diameter, maybe we increase or decrease the thickness. And the first step we're going to have to do is remesh the changes that we made. Quickly go through, remesh, and then hit run. And go back and see the results. See whether or not we're going to get something that's better or worse than what we had before. And again, we're looking at what's the maximum velocity that goes through the center of that turbine down here, velocity mid. And we want to know the overall drag force. And again, as you can imagine, it would probably take many hours for an engineer to sit around here and just remesh, rerun, remesh, rerun to find an optimal shape.
Wow. That is
so
cool.
Again,
Sorry.
So again,
This is the first time I'm sorry, Clay. This is the first time I've seen it. It is really cool. Go ahead.
So again, we set up a design study shown right here. And this time, before we were doing a single point study, this is called a multi-objective study because we wanted to both look at increasing the velocity through the middle and decreasing the overall drag force on that entire cowling. And what you end up, and again, you've got your input parameters, the 6 dimensions that I had mentioned before, and you define your responses, those 2 points. You can define as many responses as you want. And we ran through, I think, 120 different design iterations. And on the input parameters, you set like, this is the baseline parameter, this is a range I want you to look at, because that original sketch was a lot of geometric constraints. There are points that would come up with a nonsensible geometry. When you hit one of those points in here, it just throws it out, skips over it, and goes on to the next one. It doesn't hang up the software. So it really reviews the space automatically for you. And you can see down here, we started off on this baseline design right here, and this was just me eyeballing it. And we had a 5 meter per second wind inlet, so this is about a 30% increase in the wind velocity. So you can see there's great gains in just a design point right here that hits, you know, a higher velocity and also reduces the drag force. If we could handle the same drag force we started off with, we got an even better design up here. And again, we can open up any of these designs and look at what the shape is that it was analyzing, and also go back and extract the parameters for that design. That's kind of where we are with those 2 demonstrations.
Wow. I got to say, your wind turbine is really cool.
Thank you.
That was, interesting. We may have to do something with that someday.
Yeah.
Did you find anybody doing optimization like that on this, or did they just present, you know, this concept?
The first paper I found, there was, you know, a little bit of an optimization study, but it looked like a grad student just picking around 4 or 5 variable cases to figure out what's the best. This paper here that I referenced this design from, it's more or less just a review of that fuser augmented wind turbine technologies.
We'd have to send this to. We have a colleague at the National Renewable Energy Laboratory in Golden.
Oh, okay.
That they use STAR. He came out of Portland State, and then
oh, good.
Yeah, and then he moved on to got a more intense job at NREL. So interesting. Okay, that's it, isn't it? We don't even have a slide. Like,
yep.
That's
it.
Good. I like that. Well, guys, we try to keep these things short. You know, we hit our target. We're what, 45 minutes? Perfect. So, as I said earlier, hey, if you got questions, ping in, talk to Jeremy. He'll reach out, find the right person to hook you up with. And thanks for your attention very much.
Thank you.
Bye-bye.
Bye.